Hello and welcome to part 4 of pumps in PEL. So again, our little sketch just reminds us where we're up to. We've got a little vessel here, zero atmospheric pressure, a liquid worth of water in there, a 2-meter drop into our pump, and then go up into our vessel. We've got a 5-meter rise. And that's a fairly simplistic system, but we were trying to work through this problem and look at this pump. Where we got to at the end of the last 5 minutes short was we've got our system curve. So we can see our pump curve, we've got our system curve, and where the two meet, we've got our duty point. So a couple of things we might want to then think about. One would be our NPSH, and the other one might be our pump power. So NPSH, where we're looking here, if we go to Capri, equipment, pump NPSH, that's the sheet there. Again, a fairly simple sheet to fill in. So we've got our physical properties, density, viscosity, vapor pressure. The mass flow rate I've picked up from our duty point. We've got some pipework length, diameter, the roughness, that's the same as we've had before, and the K value is the same as before. The pressure above the liquid in the vessel is atmospheric, so 1 bar absolute. We've got 3 meters worth of liquid above that pump suction, so 2 meters worth of pipe, 1 meter in the vessel. And then we need to understand what the NPSH required is. So the way I did that was I went back to the catalogue, got a slightly different looking chart to the one we got before. But again, you can see here, it's got NPSH required lurking in the bottom here. So what I would have done in the graph reader is I'll set my extent to this point here and this one here, because I want to read this axis now. So I want to go between 0 and 10. So I'd set those two as the axis, 0 and 10. Flow rate as before, remembering that the gallons per minute is US gallons per minute. And then I created an equation for that curve, which is what's happening in here. So again, I can do the flow rate, that can produce my NPSH. Beautifully, it's in feet. So I then need to then convert that into meters. So again, I've used that convert value function. There you can see the equation I've put in from the graph reader, and then that's a value that we're picking up in terms of our flow rates. So that would mean giving my NPSH required. This bit here is giving me calculate a Reynolds number, a friction factor. It's working out that frictional pressure drop into the suction of that pump. So what's that pressure going to be at the suction side? It's coming out at 11.15 meters. I need 0.77 meters, so I'm absolutely fine. I'm not going to have cavitation. So that's how you would use that sheet, or one way you could use that sheet, just to check your NPSH. The final bit would be that pump power. So how much power is the pump generating? And this got a little bit interesting when I was doing this example, because this is going to take us right back to the very start of this example, and maybe an easier way of doing at least the start of this particular way of looking at pumps. But we're looking at pump power. So again, density, viscosity, flow rate. I've assumed the pump efficiency as before. This here now specifies my inlet and outlet side. So 3 meters on the inlet, 10 meters on the outlet. Again, we've got diameters, roughnesses, got some K values in there, 3 and 15, just to be consistent with what we had before. We've now got height from grade. So that's the top of my liquid level. Is that 2 meters plus the extra meter in the suction vessel? So it's 3 meters on the suction side, 5 meters on the discharge side. So we're going up that 5 meters. And then with the pressures the same in either of the vessels. So again, the green stuff's where it's doing the calculations. But we've got our Reynolds numbers, frictional losses. It's giving us our frictional pressure drop, our elevation rise, differential, pressure rise, and it's actually then worked out the required head of the pump in this calculation. So when we went all the way back at the start, what we were doing, the first thing we actually did was we wanted to work out what the delta P across this pump is and what the head needs to be with a particular flow rate. And we calculated that out. We could have just used this and picked up a value in there. So different sheets give you different values. And, again, head from pressure, a little formula there for working out. Now, if you've got a pressure, we can use a head, what that head might be. So different calculations, we can always twist them a little bit to give us different answers depending on what we're trying to achieve. But a particular one, we've got our head, and then from there we can work out the work and the power requirements for the pump. So we now know how much power that pump needs to do. And that would kind of get us through as much as we're going to do in Capri. The next step after this is then to look at FlowNet, because that's the other way of doing this, and see how these two compare and how we would do it in FlowNet. So that will be the next stage. Thank you very much.